So, in the last lecture we were examining turbulent flow in a pipe, and I had the picture of turbulent flow is as follows. In a turbulent flow there are eddies of all sizes ranging from a large scale which is comparable to the pipe diameter down to a small scale which is called the Kolmogorov scale. The large scale motion is has velocity and length scale comparable to the average velocity and the pipe diameter. The total rate of dissipation of energy, the rate of dissipation of energy per unit mass is an intensive quantity, and that can be estimated as the average velocity cubed divided by d, because that has to be equal to the power that is put in at the large scale. And the smallest scales in the flow, called the Kolmogorov scale, are estimated from the following assumption. The size and the velocity of the small scale eddies are so much smaller than the size and velocity of the large scales that the small scale eddies, their size and velocity, do not depend directly on the large scale velocity and the pipe diameter, but rather they depend only upon the rate of input of energy per unit mass or the rate of dissipation of energy per unit mass, because it is at this small scale that all the energy is dissipated. On that basis, we had estimated what are the size, the time scale and the velocity scale, the length, time and velocity scale for the smallest scale eddies, just from dimensional analysis and the assumption that these depend only upon the energy dissipation rate per unit mass and the kinematic viscosity. Kinematic viscosity is important because the energy is dissipated due to viscous effects at these small scales. And on that basis we had derived expressions for the Kolmogorov scale. The Reynolds number based upon the Kolmogorov scale is 1. Okay. Even when the Reynolds number based upon the flow velocity and the pipe diameter is very large, the flow itself creates smaller and smaller scales, such that at the smallest scale the Reynolds number based upon the Kolmogorov scale, the velocity and the kinematic viscosity, that is always 1. Okay. If you increase the Reynolds number, the smaller scale size will become smaller still, but that Reynolds number will remain order 1. The kinetic energy is primarily in the large scale flow. Okay. The kinetic energy is primarily in the large scale flow, whereas the dissipation rate of energy is primarily due to the smallest scales, okay, because the small scales flows are the small scales are created within the flow so that they can dissipate all of the energy that is put in at the large scale. And the physical picture is that energy that is being put in due to the pressure difference across the ends of the pipe, that gets transferred from the large scale eddies down to smaller and smaller scales until it is finally dissipated at this smallest scale eddy that is comparable to the Kolmogorov scale. Okay. And because the smallest scales are much smaller than the large scale, okay, however, the Reynolds number based upon the small scales is order 1. Okay. That means that the energy that is put in at the large scale passes through almost unchanged through this cascade of eddies, okay, until at this smallest scale the energy, the rate of dissipation of energy becomes comparable to the energy that is being put in per unit time, and all of that energy gets dissipated at this small scale. So, that is the physical picture. And I had also told you that the smallest scale eddies are always much larger than the molecular sizes, the molecular mean free path and the molecular velocity for a gas, or the mean free path for a gas or the molecular dimension for a liquid, okay, in the limit of low Mach number for an incompressible flow. the smallest turbulence scales are always much larger than the molecular scales. Okay. So, the picture that I have sketched out for you here is in the bulk of the flow, okay, in the bulk of a turbulent flow. Okay. Recall that I told you that the velocity profile for a turbulent flow is flatter at the center and has steeper gradients at the wall in comparison to a laminar flow. Okay. It has a steeper gradient at the wall and it is flatter at the center in comparison to a laminar flow, okay, where this is the average velocity, okay, and this is the pipe diameter. Okay. So, in this region where the velocity is nearly a constant, okay, what I will call the bulk of the flow, in this region where the velocity is nearly a constant, what I will call the bulk of the flow, in that region you have transport of energy due to turbulent eddies. Okay. And I should note that the fluctuations in the large scale flow are in general not isotropic. Okay. Typically, the velocity intensity of the velocity fluctuations in the streamwise direction for the large scale flow will be much larger than those in the cross stream direction, okay, typically. However, the velocity fluctuations in the small scale flow are nearly isotropic. In other words, the intensity of the velocity fluctuations are the same in all three directions for the small scale flow. Okay. So, this picture is valid for the eddies in the bulk of the flow, okay, away from the boundaries. Okay. What happens as you approach the boundary? Okay. As you approach the boundary, because of the no slip condition and the no penetration condition, okay, because of the no slip condition and the no penetration condition, the velocity has to necessarily decrease to 0 at the boundary. The total velocity has to decrease to 0, which means that the average velocity has to decrease to 0 and the fluctuating velocity has to decrease to 0 at the boundary. Okay. So, very close to the boundary, the transport cannot take place due to turbulent eddies, because the intensity of the velocity fluctuations has to decrease to 0 very close to the boundaries. Okay. Therefore, diffusive transport, viscous transport has to be dominant very close to the boundaries where the velocity magnitude of the velocity fluctuations decreases to 0. Okay. Okay. So, what is the velocity scale very close to the boundary? Okay. If you recall, I told you that the shear stress is a linear function of position, okay, for a unidirectional flow. Okay. In this case, on average, the shear stress will be a linear function of position. Okay. It will increase as you go towards the wall. Positive force exerted on the wall, negative force exerted on the fluid. Okay. So, this is the shear stress profile. Okay. And the shear stress depends only upon the pressure gradient. Okay. From momentum balance, we know that dP by dx, okay, okay, at the wall, okay, is equal to 4 tau w by d at the wall, okay, because the velocity fluctuations have to decrease to 0 very close to the surface. What is the relevant velocity scale very close to the wall? Okay. If the distance from the wall is much smaller than the pipe diameter, okay, if the distance from the wall is much smaller than the pipe diameter, okay, so if I expand this up, okay, I have this velocity increasing linearly close to the wall, okay, because I told you that when you come very close to the wall, ultimately it is viscous diffusion that has to dominate, because the velocity fluctuations decrease to 0. That means that the velocity has to increase linearly from the wall. And if the velocity increases linearly, then the shear stress is approximately a constant in this region. Okay. the shear stress is approximately equal to the wall shear stress in this region, which is the viscosity times the velocity gradient. The gradient in the mean velocity, okay, tau w is equal to mu times dvx average velocity by d, call this as x, and I will call this as the z direction, okay, perpendicular to the wall. Okay, so, I put a coordinate system at the surface where x is the streamwise direction and z is the direction perpendicular to the wall. So, very close to the surface, if transport is purely due to viscous diffusion, the wall shear stress has to be equal to the viscosity times the gradient in the mean velocity dvx by dz at the wall. Okay. What is the relevant velocity scale close to the wall? Okay. If you are sufficiently close to the wall where the mean velocity is much smaller than the maximum velocity, okay. If you are very close to the wall where the velocity has not yet increased to the maximum velocity, okay, then you can get a velocity scale from dimensional analysis as v star is equal to tau w by rho per half. Okay. This is just from dimensional analysis, and the assumption that the velocity is approximately, I am sorry, the wall shear stress is approximately a constant very close to the wall. Okay. This is called the constant stress layer, okay, very close to the wall. So, the velocity is approximately a constant very close to the wall. Right. Then I can assume that it is only the wall shear stress that can generate a velocity scale. That velocity scale is the friction velocity, which is the wall shear stress divided by the density. Okay. You can verify that this has dimensions of velocity. Stress has dimensions of mass, length inverse t power minus 2, force per unit area. Okay. Density has dimensions of mass and length power minus 3 whole power half. Okay. This will turn out to be equal to LT inverse. It has the same dimension as velocity. So, very close to the wall, the relevant velocity scale is the friction velocity, okay, is equal to tau w by rho whole power half. Okay. In the layer of thickness much smaller than the pipe diameter, where the wall shear stress is approximately a constant value, okay, within this thin layer. Okay. If you are sufficiently close to the wall, the shear stress will be approximately equal to the wall shear stress. Okay. Now, what is the wall shear stress? It is given by the velocity gradient close to the wall. Okay. As I said, in the bulk of the flow is turbulent, and therefore, transport takes place due to turbulent eddies. However, as you come closer to the wall, the velocity fluctuations have to decrease to 0 at the wall. Okay. As you come closer to the wall, the velocity fluctuations have to decrease to 0 at the wall, and if the velocity fluctuations decrease to 0, momentum transport is due to molecular diffusion, due to viscosity. Okay. So, in this region, the velocity scale is v star. Is equal to the square root of the ratio of the wall shear stress and the density. Okay. And because there is viscous transport here, there is also kinematic viscosity. Which is new. Okay. The kinematic viscosity is relevant in this region because here the velocity scale, the transport is due to molecular diffusion. Therefore, kinematic viscosity is of significance here. Okay. If this length scale is much smaller, okay, if this length scale is much smaller than the pipe diameter, then the pipe diameter is no longer a relevant parameter within this region. Okay. The pipe diameter is no longer a relevant parameter within this region if the thickness of this region is much smaller than the pipe diameter. And what it means is that the thickness of this region can depend only upon this wall shear stress or the friction velocity and the kinematic viscosity. Okay. And there is only one way that you can get a length scale is equal to nu by V star from the friction velocity and the kinematic viscosity. Okay. So, this the distance from the wall I have labeled as Z, I can call it as R minus R, where R is the pipe diameter and R is the radius. Okay. So, at a particular location the distance from the wall is equal to the total pipe radius minus the radius to that point in the flow. Okay. Okay. So, therefore, I can define a scaled velocity. Okay. Okay. It is called okay. So, this region where the wall shear stress is approximately a constant and where transport takes place due to viscous diffusion, it is called the viscous sublayer. Okay. And the length scale here is called a wall unit. Okay, the length scale here is a wall unit, and the reduced velocity, the scale velocity, the scaled velocity in this case is equal to the average velocity divided by the friction velocity, and the scaled length is equal to the distance from the wall R minus R divided by this wall unit, this length scale u by V star. I will call this as W plus and this as Vx plus. Okay. These are called the inner scalings, the scalings very close to the wall. Okay. In these inner units, what is the velocity profile close to the wall? Okay. I know that very close to the wall I should have the wall shear stress is equal to mu times dVx by dr. Okay. Okay. And therefore, I know that the wall shear stress can be written from this relationship. Okay. The wall shear stress is equal to rho V star square is equal to mu into dVx by dr. Okay. And if I divide throughout by rho V star square, I will get this 1 is equal to mu by rho into 1 by V star square dVx by dr. Okay. Just rewriting mu by rho as the kinematic viscosity. Okay. And this you can easily verify is going to be equal to dVx plus divided by dW plus. Okay. This one. Okay. What that means is that expressed in terms of inner units, velocity scaled by the friction velocity V star and length scaled by the wall unit nu by V star, the velocity gradient at the wall in these scaled units is identically equal to 1. Okay. So, therefore, this slope when expressed in terms of this divided by nu by V star and the velocity scaled by V star, okay, that will be equal to 1, okay, where W is equal to the distance from the wall divided by a wall unit. Okay. So, within this viscous sublayer you would expect, because there is no transport due to viscous fluctuations, the only velocity scale is this friction velocity, the wall shear stress divided by density to the half power, and the only length scale is nu by V star, okay, where V star is the friction velocity. Therefore, if I scale the density, I am sorry, the mean velocity and the distance from the wall in this manner, I will get a linear profile close to the wall. This linear profile, okay, is equal to 1, is actually observed in real turbulent flows for, okay, when the distance from the wall is less than W plus less than about 5, okay, very close to the wall, okay, you get this linear profile in the viscous sublayer. Okay, this is what is called the viscous sublayer. Close to the wall. Okay. And it is found that the velocity follows a logarithmic law. Okay. Let me just write it here. Okay, the mean velocity follows a logarithmic law Vx plus, okay, plus a constant. Okay. Okay. For about 30 less than or equal to W plus less than or equal to 200. Okay. And this is called the logarithmic layer. Okay. And in between the viscous sublayer and the logarithmic layer, there is a buffer layer for 5 less than or equal to W plus. Okay. Okay. So, if I plot the mean velocity very close to the wall, okay, if I plot the mean velocity very close to the wall in log, okay, on a log linear plot, okay, log of W plus versus Vx plus, okay, on a log linear plot. In the viscous sublayer, the velocity is a linear function. Okay. In the viscous sublayer, the velocity increases linearly with distance from the wall. Okay. So, in this log linear plot, you will get something that goes like this. Okay. And then in the logarithmic layer, this will be a straight line, because this Vx plus is equal to 1 by k times log of W plus. Okay. The first observation, that dVx plus by dW plus is equal to 1 in the viscous sublayer, that is an exact solution. Okay. I just derived it for you over here. Okay. I just derived it for you over here. This is an exact solution very close to the wall, based on the assumption that the amplitude of the velocity fluctuations decreases to 0 at the wall. Okay. Based upon the assumption that the amplitude of the velocity fluctuations decreases to 0 at the wall, you can show that the slope of the velocity profile when expressed in inner units is equal to 1. Okay. And in a turbulent flow, it is observed that this is actually a linear profile for W plus, the distance from the wall scaled by the inner unit, by the wall unit, when that is less than 5. This is a relation from experiments which can be justified by matched asymptotic expansions which are currently beyond the scope of this study, you can show that the velocity profile has to have a logarithmic behavior in an intermediate region, okay, in an intermediate region away from the wall layer. The constants in this equation have to be determined by fitting with experiments. Okay. And in experiments it is observed that this constant kappa is approximately equal to 0.41 and the C plus is approximately equal to 5 close to the wall. Okay. Okay, so these two constants. Okay. You can get the form of this equation by matched asymptotic expansions, but the values of the constants have to be fitted to experimental results. Okay. And these are considered to be universal constants, though I should point out that this area is an area of active research still, and it is quite likely that these limiting cases will change as more and more research comes out. This is the classical picture: viscous sublayer for distance less than 5 wall units, logarithmic layer between 3 and 200 wall units approximately, and a buffer layer in between those two, okay, between the viscous sublayer and the logarithmic layer. Okay. And then beyond about 200 you go to the bulk of the flow. Okay. Beyond about 200 you go to the bulk of the flow, where the velocity gradient is approximately equal to 0, the velocity is nearly flat. Okay. So that is the picture of the turbulent flow. Okay. The viscous sublayer, the buffer layer and the logarithmic layer. Okay. The first of these, the viscous sublayer, is an exact solution. If you scale the velocity by the friction velocity and the distance by the wall unit, okay, it just follows from simple definitions. Logarithmic layer is an observation that can be justified by asymptotic analysis. Then there is this buffer layer in between. Okay. And we can make an estimate of what these length scales are. Okay. For example, consider a flow, okay, a pipe flow for which the Reynolds number is equal to 10 power 5. Okay. And the friction factor is equal to 4.5 into 10 power minus 3. Okay, that is the friction factor. Okay. Note that this friction factor is much higher than that for a laminar flow. If the flow were laminar, it would be 16 by Re, which is 1.6 into 10 power minus 4, whereas since the flow is turbulent, the friction factor is much higher. Okay. The wall shear stress, okay, is equal to the friction factor times the kinetic energy per unit volume. Okay. That is the definition of the friction factor. Friction factor is wall shear stress by kinetic energy per unit volume. However, from our definition of the friction velocity, this is also equal to rho times V star square. Okay. And this gives us the relationship between V star and the average velocity. V star is equal to VAV into F by 2. So, the friction velocity is equal to the average velocity times the square root of the friction factor by 2. Okay. What that means is that the ratio, okay, the Reynolds number based upon the friction velocity, okay, if you calculate a Reynolds number based upon the friction velocity, that is going to be equal to the Reynolds number based upon the average velocity into root f by 2. Okay. In this particular case, this Reynolds number is about 4743. Okay. Now, you can also get the ratio of the wall unit by the diameter. The wall unit was equal to nu by u star from dimensional analysis. nu had dimensions of length square per time, velocity had dimension of length per time, into 1 by diameter. Okay. And you can easily see that this is equal to inverse of the friction velocity, Reynolds number based upon the friction velocity, okay, because mu by rho is just the kinematic viscosity. Okay. So, this is equal to 2.1 into 10 power minus 4. Okay. So, for this flow at a Reynolds number of about 10 power 5, the wall unit is 10 power minus 4 smaller than the pipe diameter. Viscous sublayer is within distance of 5 times the wall unit. There is about 1,000th, okay, 1,000 times less than the pipe diameter. So, the viscous sublayer is confined to a very thin region, 1,000 times less than the viscous than the pipe diameter, close to the wall. And the buffer layer goes to about 200 times the viscous, which is 200 times the wall unit. And 200 times the wall unit would be approximately 1/100th or 5 by 100 of the pipe diameter. So, these occupy a very thin region very close to the wall, okay, the viscous sublayer and the buffer layer. And in the bulk of the flow you have a turbulent flow, which I had described for you physically in the last lecture. So, therefore, the structure of turbulence is in the bulk of the flow there is transport due to turbulent eddies with sizes ranging from the large scale, the pipe diameter, down to the smallest Kolmogorov scale. When you come close to the wall, the fluctuating velocity has to decrease to 0. There is a viscous sublayer where transport is primarily is due to momentum diffusion, where transport due to convection is negligible. In this region, the relevant length scale is the friction the relevant velocity scale is the friction velocity. In this region, the relevant length scale is the wall unit, nu by v star. The velocity gradient expressed in terms of the friction velocity and the wall unit has to be equal to 1 in this viscous sublayer. There is a buffer layer where there is a logarithmic law, and then there is a outer region where the flow is fully turbulent. So, this is a brief description of turbulence, the energy cascade in turbulence, the Kolmogorov scales in the bulk of the flow, and the turbulent structure very close to the wall. So, this completes our discussion of turbulence in a pipe flow. The next lecture I will start looking at oscillatory flow in a pipe. I will continue this in the next lecture. I will see you then.